We turn now to the motion of guest molecules in copper BTC. The structure is rather interesting and fascinating. It consists of large cages separated from adjacent large cages by 9 angstrom windows. The large cages are also connected to tetrahedral pockets through openings that are about 4.6 angstrom in size, and the openings are triangular in shape. There are 8 tetrahedral pockets per unit cell. Let's have a look at the animations for methane motion within the cage window structure of copper BTC. The methane molecules are able to enter the tetrahedral pockets through these triangular 4.6 angstrom windows. MD simulation data for the self-diffusivity of methane in copper BTC as a function of loading is shown by the red circles. Interestingly, at a loading of 32 molecules per unit cell, the self-diffusivity of methane exhibits a maximum in the Now, the tetrahedral pockets are preferred locations for methane, and since there are 8 pockets per unit cell and the maximum loading per pocket is 4 methane molecules at a total loading of 32, all the preferred locations within the tetrahedral pockets are fully occupied. An increase in the loading of methane will force methane molecules to occupy the large open cages. In large open cage structures, the diffusivity invariably decreases with increased loading. Further explanation of the reasons behind the maximum and decrease is provided in this article. The isosteric heats of absorption are plotted by the green squares here, and up to a loading of 32 molecules per unit cell, we see that the isosteric heats of absorption are higher due to stronger interactions with the walls of the pockets, and then the isosteric heats of absorption tends to plateau out because the interactions of methane with the large cages is less strong. Animations showing the motion of ethane, propane, normal butane, and normal pentane show that all these linear alkanes can enter the tetrahedral pockets by entering it in a lengthwise manner. The tetrahedral pockets are also preferred locations for these linear alkanes, but the maximum loading per pocket decreases with increasing chain length, and the data on the self-diffusivities of C2, C3, NC4 and NC5 also show a maximum at a certain loading, and that loading at which a maximum occurs is different for each molecule because the maximum capacity within the tetrahedral pockets decreases from C2 to NC5. Let us have a look at the motion of isobutane, neopentane, and 2-methylbutane within CuBTC. Due to their configurations, the branched alkanes have greater difficulty in entering the tetrahedral pockets because of the constraint offered by the 4.6 angstrom window. The diffusivities of these branched alkanes are significantly lower, therefore, than the diffusivities of the linear alkanes shown in the previous slide.